Deep beneath our feet, there is a seam in Earth's memory where the rocks suddenly change color. It is a thin line, roughly the thickness of a coin, laid down about 65 million years ago, when something violent rained a storm of glassy beads across the planet. So here is the unsettling question: if we were not the first species to master fire, metals, and the physics of atoms, what would be left of our predecessors after tens of millions of years? Not their cities, not their bones in neat museums. Time would grind them down, subduct their continents, recycle their seafloors, and fold their roads into mountains. Yet certain fingerprints, subtle, global, geochemical, could persist. Could we be walking every day on top of the last faint signatures of a civilization that came and went long before ours? This idea has a name: the Silurian Hypothesis. It does not claim that ancient engineers built power plants alongside dinosaurs. It asks a scientific question: if an industrial civilization had once risen and fallen deep in geological time, could the rock record tell on them? What should we look for? And, more importantly, would we even recognize the evidence if we found it? To answer that, we have to think like the planet, not like archaeologists. Archaeology can retrieve pottery from thousands of years ago, shipwrecks from millennia ago, and even tools from the edge of the last ice age. But push farther back hundreds of thousands, millions of years, and the surface of Earth becomes a conveyor belt. Wind, water, and biology erase. Plates dive, oceans open and close. Over those time scales, only global signals survive. Shifts in carbon isotopes, bursts of certain metals, odd molecules that do not fit the usual patterns, and abrupt changes in sediments that point to rapid warming, sudden acidification, or a mysteriously oxygen-starved ocean. Imagine a timeline of Earth as a long night highway seen from space. A city illuminates the road for a moment, then the lights go out. From orbit, you would not see the abandoned buildings. You would see the faint afterglow on the clouds. For a technological species, that afterglow might be a sharp, planet-wide change in the ratio of carbon-13 to carbon-12, the isotopic accent of fossil fuels released in a geological instant. It might be nitrogen compounds washed from synthetic fertilizers, or a pulse of heavy metals that shows up in river deltas and lake mud on every continent. Consider plastics. On human timescales, they feel permanent. On geological timescales, they are food for pressure and heat. But plastics do not merely vanish. In beaches and dunes today, we already see plastic fused with sand and lava into a strange rock called plastiglomerate. Given enough time, that material could be ground and buried and cemented into new sedimentary layers. If something like this had happened ages ago, if a past civilization ever mass-produced synthetics, its legacy would not be junkyards and landfills, but polymer ghosts locked into stone. Then there is radiation. Modern nuclear tests leave unmistakable isotopic breadcrumbs, peculiar ratios of plutonium and cesium, for example, that can be measured decades later. Over millions of years, those signatures decay, but their daughters, their distribution patterns, and the glassy microspheres formed in blasts still tell a story. The KPG boundary spherules we find today are from an asteroid impact, not a bomb. Yet, the fact that energy-dense events can leave glass and odd isotopes scattered worldwide reminds us that any civilization tapping extreme energies will write itself into the rocks. None of this is proof that someone came before us, but the fact that such signals exist and that we are currently imprinting them ourselves turns the hypothesis into a testable framework. If you wanted to hide a civilization from deep time, you would have to hide from the laws of thermodynamics. You would need energy, and energy leaves marks: heat, chemistry, waste, and abrupt transitions in layered stone. Over the next chapters, we will treat Earth like an ancient crime scene. We will examine mass extinctions that arrived not with a single asteroid strike, but with long, feverish episodes of carbon release and ocean suffocation. We will look for industrial tells that could masquerade as natural events, and for natural events that look eerily industrial. We will ask whether nuclear signatures could survive long enough to cross deep time, whether plastics can metamorphose into the rock cycle, and whether metal spheres in ancient clays really are only the fingerprints of meteorites, or could ever be something more. Before we dive in, a caution. Extraordinary claims demand cautious language. The Silurian Hypothesis is not a conspiracy theory. It is a thought experiment designed to sharpen our tools. It forces us to ask better questions of the rock record and to understand the limits of preservation, and it holds up a mirror to our present moment. If we disappeared tomorrow, what story would the next tenants of Earth read in the strata? Would they find a single thin line like the one that marks the end of the Cretaceous, rich in odd metals and sudden changes, or would they see a broader, messier band, a signature of centuries-long industry and its aftershocks? Keep that thin line in mind as we begin. The rocks do not care about myths, they care about physics and chemistry. If anyone came before us, their truest ruins would not be temples or towers, but ratios and residues buried in clay and chalk and the quiet arithmetic of stone. To follow this idea, we first have to understand what time does to evidence. If you wanted to erase a civilization, you would not need a catastrophe. You would let weather, biology, and plate tectonics do their work. Rain would gnaw at concrete. Plant roots would pry open asphalt. Freeze and thaw would shatter steel. Rivers would grind the remains to silt and carry it to the sea. There, mud would bury the fragments, squeeze them, heat them, and in some places, drag them down a subduction zone. That is Earth's shredder, slow on human clocks, ruthless on geological ones. The youngest skin on Earth is the seafloor. It spreads from mid-ocean ridges and dives back into the mantle at trenches, which means almost none of it is older than 200 million years. Anything built on ocean crust is short-lived by default. Even on land, the record is harsh. Mountains rise and weather away. Deserts migrate, glaciers, sandpaper continents. Over millions of years, only certain quiet places keep secrets. Lake bottoms with fine sediments, deep ocean basins where the water lacks oxygen, caves sealed from groundwater, and rare, rapidly buried floodplains. So what actually endures? Not skyscrapers or smartphones. Chemistry endures, ratios endure, patterns endure. Picture the rock record as a ledger written in atoms. On every page there are entries, the ratio of carbon-13 to carbon-12, nitrogen-15 to nitrogen-14, oxygen-18 to oxygen-16. A sudden, global change in those numbers is like a line of red ink in the planet's accounts. Industrial civilization is making such a line now by burning fossil carbon, because ancient plants preferred the lighter isotope. The carbon they stored and we release carries a distinctive, measurable tilt. There are other tells. Industrial agriculture rearranges nitrogen on a continental scale. Synthetic fertilizers push nitrates into rivers, estuaries, and coastal shelves, triggering oxygen-poor dead zones. When oxygen drops, the bottom mud grows dark and organic rich, often sprinkled with tiny pyrite framboids, little raspberries of iron sulfide that form when microbes thrive without oxygen. Those layers preserve a chemical time capsule of the water above them. If something similar happened deep in the past, the rocks would remember it. Metals also leave tracks. We mine, refine, and concentrate elements that are normally scattered. Aluminum, copper, rare earth elements, and the platinum group metals. We then disperse them in wiring, batteries, catalysts, pigments, and dust. Corrosion returns many of these to oxides and salts, but not evenly. Where industry piles metals together, harbors, landfills, river mouths, smelter sites, sediments can trap unusual concentrations. Give those pockets deep time, and they can resemble ore layers, but their mix and distribution tell a different story. Then come synthetics. On some beaches today, bits of plastic fuse with sand and ash into a strange rock called plastiglomerate. Buried and warmed, polymers crack into simpler hydrocarbons, carbonized residues, and stubborn microplastic grains. Some fragments get locked inside mineral crystals or clay lattices. becoming tiny inclusions that ride the rock cycle far longer than any bottle ever would. A far future investigator might not find a recognizable object, but they could find microscopic spheres, fibers, and polymer ghosts trapped in stone. What about radioactivity? Nuclear detonations and reactor leaks make isotopes in proportions that nature rarely does. Some decay quickly, but their daughter products and their distribution through the environment are like fingerprints. Glassy fallout beads can be trapped in sediment. Peculiar xenon isotopes can be sealed inside minerals. Unusual ratios among the daughters of plutonium or uranium can persist in closed basins like lake beds and peat bogs. After tens of millions of years, the trail would be faint, but not necessarily gone. There is also climate. Civilization is a heat engine, and heat engines leave wake. Rapid greenhouse warming, ocean acidification, and shifting rainfall and fire patterns all leave traces. You see charcoal spikes from continent-wide burns. You see pollen change as forests retreat and grasslands advance. You see marine shells that grew thinner because seawater absorbed extra carbon dioxide and nudged acidity upward. Natural events can mimic these signals, flood basalts and methane releases, but they come with their own calling cards. Careful does not mean vague. The question becomes, what package of clues would be hard for purely natural processes to assemble, but quite natural for an industrial civilization to produce? One criterion is multiplex evidence. A single dataset can mislead, but when independent lines converge carbon, nitrogen, sulfur, and oxygen isotopes, trace metal patterns, microplastic residues, or their metamorphic descendants, anomalies in radionuclides, and the physical story told by sediment textures, you get a stronger case. A second criterion is synchronicity. Industry spreads fast. An active civilization would imprint lakes, rivers, reefs, dunes, and even cave deposits at roughly the same time, rather than stepwise over hundreds of thousands of years. A third is context. If a suspected signal lines up with known volcanic provinces, impact layers, sea level swings, or the opening of an ocean basin, the natural explanation wins. If it does not, if the chemistry looks global and abrupt, but the usual triggers are missing, then the case stays open. And there is the absence test. If an industrial-like signal appears, we should also look for artifacts and fossils in the same layers. The lack of anything technological would not disprove industry. The shredder is real, but it would push us toward natural causes. If, however, the signal arrives with odd mineral forms, melted sands, or synthetic-looking residues that do not fit known volcanism or impacts, the weight of evidence begins to tilt. This is our roadmap. First, we will assemble a checklist of geological fingerprints a civilization cannot help but leave. Then, we will tour Earth's ancient crises and ask how well they fit that list. Along the way, we will learn something humbling: how loud a civilization must be to be heard through stone, and how quiet it would need to be to pass without a trace. We are not hunting myths. We are auditing the planet's ledger to see whether the books ever recorded someone like us before we arrived. If we want to know what to look for, the cleanest reference is ourselves. Imagine a geologist, 50 million years from now, slicing into a cliff that was once our century. They would not see a city skyline. They would see a band. Within that band, grains and atoms would tell a story about a species that briefly ran a planetary heat engine. Start with carbon, because energy begins there. Fossil fuels carry a light isotopic accent, a slightly lower share of the heavy carbon-13 compared to the carbon you find in the air and oceans. When burned quickly, that accent shows up as a global negative swing in the carbon-13 record, like a sudden detuning of the planet's music. It is already visible in modern sediments. Deep time blurs fine details, but not the direction of the trend. If an earlier civilization ever tapped ancient carbon at industrial scale, the rocks would record a sharp, rapid dip years to centuries in actual time spread across lakes, shelves, and deep-sea muds. Now flip to nitrogen, the quiet partner in food and fuel. Industrial fertilizer breaks the natural bottleneck that kept life on a leash for billions of years. With enough fertilizer, rivers carry excess nutrients to coasts, oxygen slumps, and microbes rewrite the chemistry of the water. The result is dark, organic-rich layers that trap a telltale pattern. Nitrogen isotopes shift, tiny iron sulfide, raspberries appear, and certain sulfur compounds rise. That package nutrient spike, oxygen crash, microbial bloom forms a diagnostic rhythm you can read in cores. It does not prove industry, but it is a signature industry easily makes. Metals leave fingerprints too. We dig, refine, and scatter elements that geology usually keeps diluted: copper, lead, nickel, chromium, rare earths, and platinum group metals. Combustion and smelting loft ultrafine particles that drift for thousands of kilometers and fall as dust. In many modern sediments, you can already measure a mid-20th century jump in lead and other trace metals. Given millions of years, some of those will migrate or be locked into new minerals, but the overall anomaly, its timing, its global reach, its peculiar mix, should persist as a faint but coherent chord in the strata. Soot writes with magnetism. Engines and fires yield microscopic magnetite and soot flakes that blanket soils, bogs, and bays. Those particles align a little like compass needles and can boost the magnetic intensity of a layer. Future geologists could pick out our band with a handheld magnetometer before they ever touched a microscope. Volcanoes can do something similar, but their timing and mineral recipe differ. Industry tends to smear magnetite globally in a near-synchronic step. Volcanoes tend to spike around particular provinces. Then there are technofossils, materials that did not exist before us. Coal plants and incinerators make fly ash spheres, perfect little glass beads rich in aluminum and silicon that settle into mud worldwide. Plastics weather into fibers and grains, and fuse with sand and cinders into plastiglomerate, a new rock born on beaches and in burn pits. Over deep time, polymers crack and carbonize, but the spheres and odd inclusions can be preserved like insects in amber, obvious under a microscope, even if unrecognizable to the naked eye. If an ancient industry ever generated synthetic organics at scale, the eventual rocks might hold halogen-heavy residues and unusual ratios of chlorine and bromine in their organic matter, a chemical accent that natural kerogen rarely acquires. Radiation is a sharper pen, though it fades. Nuclear detonations and certain reactor accidents scatter isotopes, cesium-137, plutonium-239, that decay over tens of thousands of years, far shorter than geological epochs. But they do not vanish without a trace. Their daughter products, their distribution in isolated basins, and the glassy microspherules that form in some blasts can survive in sealed sediments. Even if an ancient nuclear chapter were too brief or too small to leave plutonium itself, it could still leave patterns that look wrong for lightning, volcanism, or meteor impacts. The absence of those supporting natural signatures would be the clue. Sedimentology adds the stage directions. Human land use accelerates erosion, dams trap silt, cities produce distinctive textures like angular rubble and microconcrete fragments, coastal works shift sandbars and lagoon infill. In core, that becomes a sudden change in grain size, mineral mix, and organic content, often accompanied by novel minerals created at low temperatures, phases related to cement, fly ash, and slags. Over time, these alter into carbonates and clays, but their shapes and associations stay odd, like a dialect the rock learned late in life. Biology answers back. Species move. Pollen diagrams show abrupt flips from forest to grassland and back. Domesticated animals, crops, and commensals spread across continents. In the fossil record, small creatures with short lives, plankton, beetles, mollusks, register the fastest. Their sudden appearance, disappearance, or dwarfing in a narrow layer tells you the planet's living fabric was yanked. In the sea, warming and acidification thin the shells of foraminifera and dissolve carbonate ooze, leaving a clay-rich horizon that flags a big CO2 push. The rocks remember both who lived and how hard living became. All of this must be read at the right scale. Deep-sea mud accumulates millimeters per 1,000 years. River deltas lay down sediments in pulses. Deserts store wind-blown dust in fits and starts. A civilization that lasts a few thousand years writes a thin line everywhere rather than a thick stack somewhere. That thinness is not a flaw. It is the point. Sudden, global, cross-environment change is rare in Earth's slow diary. When it happens without the usual companions, no flood basalt province, no crater, no slow drift in ocean chemistry, it deserves a closer look. So our checklist takes shape. Look for a rapid, globally coherent carbon-13 decline, paired with warming and acidification signatures. Check for synchronized changes in nitrogen and sulfur that shout nutrient glut and oxygen loss. Scan for trace metal anomalies and magnetic soot that arrive together. Hunt for fly ash spheres, plastiglomerate descendants, or polymer ghosts welded into minerals. Search closed basins for odd radionuclide legacies or their glassy proxies. Read textures for abrupt shifts in erosion, rubble, and low-temperature industrial minerals. Ask biology whether a short, sharp reshuffle of life took place at the same time. And finally, test the context. Match the timing against known impacts, rifts, and volcanoes. If those do not line up, keep the file open. With that toolkit, we can turn to Earth's past, not to prove a story we want, but to falsify the ones we do not. The planet has staged its own industrial-looking dramas before bursts of carbon, fevered seas, anoxic oceans, mass die-offs. In the next chapter, we will meet one of the strangest and most instructive, a greenhouse spasm 56 million years ago, called the Paleocene-Eocene Thermal Maximum. It looks, in some ways, like us. It looks, in other ways, like a volcano's cousin. By mapping our checklist onto its rocks, we will learn how to tell an ancient machine from a natural fire. The Paleocene-Eocene Thermal Maximum is our first big test case. It happened about 56 million years ago, long after the dinosaurs, but long before us. In a geological instant, the planet warmed by 5 to 8 degrees Celsius. The deep sea turned more acidic. Some ocean layers ran short of oxygen. On land, forests shifted, fires surged, and many mammals shrank in size. If you only looked at the broad strokes, rapid carbon release, global warming, acidification you might say, this looks uncomfortably like what an industrial civilization would do. But the details tell a different story, and learning to read those details is the whole point. Start with the carbon signature. In cores from oceans and lakes around the world, the ratio of carbon-13 to carbon-12 takes a sharp dive at the start of the PETM. Geologists call this a negative carbon-isotope excursion. It is global, it is fast by geological standards, and it points to a flood of light carbon entering the air and oceans. That is exactly what burning fossil fuels does today, which is why the PETM often gets called an ancient analog for our future. But analog does not mean copy. Our spike is happening in decades. The PETM took thousands of years to ramp up, likely in pulses, and then about 1 to 200,000 years to fade, as weathering slowly drew the carbon down again. Next, the oceans. The extra carbon dioxide pushed seawater toward acidity, which made it harder for tiny plankton to build shells of calcium carbonate. In deep-sea cores, the layer that should be white and chalky is instead thin or missing at the PETM horizon. Geologists say the carbonate compensation depth, shoaled the depth below which shells dissolve, moved upward. That trace is like a page torn from a book. Something big happened to ocean chemistry, and it happened everywhere at once. Again, it is a signal an industrial civilization could make, but other lines of evidence point toward a natural engine. Volcanoes leave clues that industry does not. During the PETM, the North Atlantic was opening. A giant volcanic province flared where Greenland and Europe were pulling apart. Sheets of magma pushed into organic-rich rocks, baking them like a hot iron on damp wood. That process can release huge amounts of carbon as CO2 and methane without any smokestacks. In rocks that captured the PETM, some sites show spikes of mercury, a tracer, often tied to volcanism. Osmium isotopes tilt toward mantle values, another volcanic accent. These geochemical hints say, look to the crust and the mantle, not to machines. What about methane hydrates, the frozen methane in ocean sediments? Many researchers think warming from early volcanic CO2 may have destabilized some of those ices, adding an extra jolt of very light carbon to the system. That would help explain how big the isotope swing is, because methane carries an even lighter signature than coal or oil. If so, the PETM becomes a two-step drama. Geology lights the match, climate tips a storehouse, and the Earth system runs away for a while. The timing, the location of volcanic sills, and the mass balance of carbon all point to this kind of cascade, not to a short, synchronized pulse that would match industry. Now, apply our checklist. Multiplex evidence? Yes. Carbon isotopes, oxygen isotopes, clay layers, dissolution of deep-sea carbonates, biomarkers of low oxygen waters, and changes in plant pollen all align. Synchronicity? The onset is quick in many cores, often less than 10,000 years, but not instant. The spread is global, yet the fingerprints are woven into a known tectonic context. The North Atlantic igneous province was active at the right time and place. Context test passed for nature. Look for technofossils. We find none. No fly ash spheres from coal stacks. No plastiglomerate or polymer ghosts welded into minerals. No odd halogen-rich residues that suggest synthetic organics. Look for radionuclide patterns that fit bombs or reactors. Again, none. The PETM horizon is missing the telltale daughters and sealed-in noble gas ratios you would expect from a nuclear age, even after decay. Instead, we find what volcanism and climate feedbacks make. Mercury ties to eruptions, osmium ties to mantle inputs, clay-rich layers from dissolved carbonates, and widespread signs of anoxic seas. Land tells the same tale. Soils in some regions suddenly turn more weathered and lateritic, as if rain and heat went up together. River systems carry more sediment for a time. As vegetation zones shift, pollen and plant waxes record a world that got warmer, wetter in some belts, drier in others. Mammals react fast. In North America and Europe, several lineages shrink. That dwarfing is a biological response to heat stress and changing food webs, not an industrial byproduct. It is a vivid lesson, but not a mechanical one. There is another difference that matters: texture. Our century stacks signals on top of each other at once. Carbon, nitrogen from fertilizers, trace metals from smelting, magnetic soot from engines, plastics, combustion fly ash, and a short, sharp radionuclide pulse from nuclear tests. The PETM is loud on carbon and climate, but quiet on metals, synthetic residues, and radiation. Its orchestra has fewer instruments. That selective loudness helps us separate a natural fever from an industrial fire. None of this makes the PETM less important. In fact, it makes it more useful. It shows how the Earth system reacts to a big carbon shove. Rapid warming, acidifying seas, oxygen loss in the oceans, migration and dwarfing on land, and a long, slow recovery governed by rock weathering. It teaches us that once feedbacks wake up, they can amplify the original push. And it reminds us that even the fastest natural events are slow compared to the century scale. If you ever found a PETM-like carbon swing that happened globally in a few centuries and came packaged with metals, plastics, magnetic soot, and weird radionuclide legacies, you would have a very different conversation. One more lesson from this case: the rock record can separate lookalikes if you ask it the right questions. When you see a negative carbon isotope excursion, do not stop there. Pull cores from many environments. Measure mercury, osmium, and other traces of volcanism. Hunt for technofossils with microscopes and mass spectrometers. Read the timing at the highest resolution the sediments allow. If the context lines up with a known volcanic province or a rifting event, favor the natural script. If the context is missing and the package looks strangely modern, keep digging. With the PETM as our calibration, we can now visit other strange chapters: oceanic, anoxic events, in the age of dinosaurs, the end Permian catastrophe that nearly reset complex life, and smaller, sharp climate jolts in the recent past. Each will sharpen the line between what Earth does to itself and what a civilization might do to it. The more we learn to tell those stories apart, the better we can read the strata for ghosts, and the clearer we can hear our own echo forming in stone. Oceanic anoxic events sound like science fiction, but they are real chapters when large swaths of the sea ran out of breath. Picture wide, shallow oceans under a greenhouse sky. Warm water holds less oxygen. Stratified layers stop mixing. Nutrients pour in. Microbes bloom. The deep turns stagnant. In those dark waters, fine mud settles into paper-thin laminations that never get churned by worms because the worms are gone. Over time, that mud becomes black shale, organic-rich rock that many modern oil fields come from. These layers are Earth's notes about suffocation, written in ink that does not fade. One of the sharpest of these episodes hit about 94 million years ago, at the boundary between the Cenomanian and Turonian ages. Geologists call it OAE2. If you opened a core from that time, you would see a sudden change to darker, finer sediments, rich in organic matter and pyrite framboids, those tiny, raspberry-shaped iron sulfide clusters that only form when oxygen is scarce. Trace metals such as molybdenum and vanadium run high. They concentrate in anoxic basins. Biomarkers molecules that once formed the skins of ancient microbes suggest that in some places the ocean's sunlit zone itself became sulfide-rich, a strange condition called photic zone eusenia. Life survived, but the balance shifted dramatically. Now read the carbon record. Curiously, OAE2 shows a positive swing in carbon-13, the opposite of the light carbon dip you would expect from a civilization burning fossil fuels. Why? Because during OAE2, the Earth system buried massive amounts of organic carbon in those black shales. Organic matter is light in carbon-13. Remove a lot of it from the ocean, atmosphere pool, and the remaining carbon looks heavier. It is a mirror image of our present-day signature. That contrast, positive versus negative carbon-13 shifts, is one of the cleanest ways to tell organic burial event from fossil carbon release in the rock record. What ignited OAE2? The context points to geology. Around that time, a large igneous province was active in the Proto-Caribbean region. Magma intruded organic-rich sediments, cooked them, and vented CO2 and other gases. Mercury in marine sediments, often a tracer of volcanic activity, spikes near the onset in many cores. Osmium isotopes tilt toward mantle values, another volcanic accent. Put together, the package reads like this. Volcanic carbon starts the warming. Warmer, more stratified seas favor oxygen loss. Nutrient feedbacks intensify blooms. Carbon burial surges. The isotopes flip positive while black shales blanket basin floors. It is dramatic and global, but its fingerprints are volcanic and oceanographic, not industrial. A similar story plays out earlier, during OAE1A about 120 million years ago. Again, we see widespread black shales, high organic content, trace metal enrichments, and hints of photic zone eugenia in some basins. Again, the timing lines up with a colossal volcanic outpouring, this time associated with the Ontong Java Plateau, one of the largest piles of basalt on Earth. Carbon and mercury take their places, osmium shifts, carbonate in the deep sea thins as acidified waters eat shells. Recovery takes hundreds of thousands of years as weathering on land drags carbon back into minerals. The tempos are long by human standards, and the suite of changes is coherent with tectonic fire rather than factory smoke. Our checklist helps keep the stories straight. Multiplex evidence? Yes. Lithology, isotopes, trace metals, biomarkers, and sediment textures all change together during OAEs. Synchronicity? The shift is quick geologically, but not instant. It unfolds over thousands of years and lasts for a significant chunk of a million. Context: volcanic provinces and rifting events match the timing. Technofossils, none. No fly ash glass spheres from coal stacks. No plastiglomerate descendants. No halogen-rich synthetic residues. No weird radionuclide patterns. Metals spike, but in patterns you get from anoxic chemistry, molybdenum and vanadium, locked into sulfur-rich muds, rather than the odd mixes you would expect from widespread smelting and catalysts. Even magnetic signals fit nature. Volcanic ash layers and diagenetic minerals can tweak magnetism, but the smooth global blanket of engine-made magnetite soot is missing. There is a deeper lesson here about how the Earth system can look industrial without any machines. Industry is, in thermodynamic terms, a way to move carbon and nutrients fast. Volcanoes and climate feedbacks can move them fast enough, too, on thousand-year clocks instead of decade clocks. Warmth weakens ocean mixing. Stratification protects anoxic deep waters. Microbes that, like sulfide, take over. Their biomarkers fill the rock. Rivers, supercharged by altered rainfall, deliver more phosphorus and nitrogen. On a planet scale, this feedback web can paint a band in stone that any future reader would recognize as a cascade. Push the system, and it flips into a new mode that buries carbon and starves the deep of oxygen. Could an industrial civilization make an OAE-like horizon? In principle, yes, by warming the climate rapidly, fertilizing coasts, and expanding dead zones, but the details would differ. A technological OAE would start with a global negative carbon-13 excursion from fossil fuel emissions, not a positive one from organic burial. It would arrive in centuries rather than millennia. It would be accompanied by a cocktail of technofossils, combustion fly ash spheres, a peak of microplastic residues, or their metamorphic ghosts, halogen-heavy organics from industrial synthesis, magnetic soot, and a short, sharp radionuclide tracer in closed basins. In other words, the anoxia would be part of a much busier band. This contrast points us toward the right kind of search. If you ever find a thin, globally correlated layer with a negative carbon-13 jolt that ramps within a few centuries in high-resolution lake or shelf records, and if that layer also carries trace metal anomalies inconsistent with volcanism, polymer inclusions in minerals, or unusual halogens in sedimentary organic matter, you should not shrug and say, probably a volcano. You should test the industrial hypothesis. Conversely, if the carbon-13 goes positive, mercury ties to volcanic provinces, osmium whispers mantle, and the onset takes thousands of years, you are looking at Earth's own hand. Where should we look hardest? Quiet basins with fine, undisturbed laminations, salt marsh peats and lake beds that trap particles gently, caves where dripstones archive airborne dust and pollutants, desert dunes that preserve microplastics and soot, and shelf seas where sediment piles quickly enough to capture century-scale wiggles. Some of these archives exist for only the last few million years, but there are ancient analogues, evaporite basins, restricted seas, and continental interiors that once held long-lived lakes. The trick is resolution. You want places that add pages fast enough to record a civilization-length story, even if the book has been pressed for tens of millions of years. When you step back, oceanic anoxic events become a calibration curve. They teach us what a natural carbon and oxygen shock looks like when written by volcanoes and feedbacks, and they set a bar for how loud a biosphere can shout without a civilization. With that bar in mind, we can now turn to the loudest natural disaster of all, the end Permian mass extinction, when nearly everything almost died. If any natural event could be mistaken for a planet-wide industrial catastrophe, it is that one. Reading it carefully will tell us how to separate the loudest volcano from the faintest machine. The end Permian mass extinction is the loudest alarm bell in Earth's archive. 252 million years ago, nearly everything almost died. In the oceans, more than 4 out of 5 species vanished. On land, most vertebrate lineages collapsed. Forests thinned to scrub. Rivers ran choked with silt. Geologists call it the Great Dying. And if any natural catastrophe could be mistaken for a planet-wide industrial disaster, it would be this one. Reading it carefully shows us how to separate the loudest volcano from the faintest machine. Begin with the carbon story. Across the boundary, carbonate rocks and organic matter register sharp negative swings in carbon-13, the isotopic signature you get when huge amounts of light carbon rush into the air and ocean. But the tempo is not the staccato of centuries. It arrives in pulses over thousands to tens of thousands of years. After the plunge, the system wobbles with aftershocks before a slow recovery. That rhythm is critical. Civilization writes thin and fast. The end Permian writes thick and pulsed. What lit the fuse was not factories, but a flood of lava. In Siberia, a mantle plume produced one of the largest volcanic provinces ever, the Siberian Traps. For hundreds of thousands of years, magma rose through crust, loaded with coal and other carbon-rich sediments. When hot rock intruded those layers, it baked them, releasing vast amounts of CO2 and methane. Some of that methane came not from volcanoes directly, but from organic matter cooked in place, a thermogenic pulse capable of pushing the carbon-13 ratio sharply downward. Think of it as a planet-scale industrial accident with no industry. Heat applied to carbon stores, chemistry doing the rest. The oceans bore the brunt. Warmer surface waters held less oxygen and mixed poorly with the deep. As circulation faltered, large parts of the seafloor slipped into anoxia. In many boundary sections, the sediments turned black and laminated, free of burrows, rich in pyrite framboids, the tiny iron sulfide raspberries that form only when oxygen is scarce. Biomarkers tell an even stranger tale. Molecules from green sulfur bacteria, organisms that thrive where sunlight meets sulfide, appear in some rocks. That implies photic zone Eocene hydrogen sulfide rising so high in the water column that poison touched the sunlit layer. This is a different planet, not a subtle tweak of the one we know. Acidification bit hard. As CO2 surged, seawater chemistry shifted and carbonate shells dissolved. Deep basins lost their white, chalky layers. Some reefs vanished outright. Rugose and tabulate corals, already stressed, failed to cross the line. The carbonate factory, the whole web of organisms that build reefs and shell-rich sediments, stumbled for millions of years. On land, plants and soils echoed the shock. Pollen and spores reshuffled. In some regions, a coal gap follows the boundary. For several million years, the steady accumulation of peat that becomes coal slowed to a whisper. That suggests landscapes too disturbed, too erosive, or too dry and fire-prone to build thick, soggy peatlands. Rivers responded by carrying coarse, angular sediment, a sign that hill slopes were stripped and vegetation was thin. Trace elements and isotopes sharpen the picture. Mercury levels spike in many end Permian sections, a fingerprint often tied to large volcanic outpourings. Osmium isotopes tilt toward mantle values. Some cores show enrichments of metals like nickel and vanadium, but in patterns that fit anoxia and volcanic dust rather than smelting or catalytic converters. In other words, the metal story matches the chemistry of suffocating seas and persistent eruptions. There is no global plume of magnetic engine soot, no synchronous, short-lived radionuclide pulse that would betray nuclear testing, no fly ash spheres from coal stacks scattered across every basin. The air itself may have changed in ways industry could imitate, but volcanoes can also achieve. When magma bakes sedimentary rocks and the eruptions vent halogen gases, chlorine, bromine, fluorine, the stratosphere can lose ozone. Some fossil leaves across the boundary show micro-damage consistent with elevated ultraviolet stress, and spore walls record chemical changes that line up with ozone thinning. That kind of atmospheric injury could accompany an industrial catastrophe, but here it arrives on volcanic schedules, and alongside every other sign of tectonic fire. Synchronicity remains a key test. At the end Permian, the worst ecological crash lines up with the heaviest volcanic activity. You can trace the pulses in lava and intrusions, and you can trace the pulses in the carbon record and the spread of anoxic seas. The onset is rapid geologically, but it is neither global in a decade nor identical across all environments. Some shelves flip to anoxia sooner, some later. Some continental interiors suffer drought and fire while others flood. A technological civilization would smear a more uniform, near-instant package of signals across the planet. Carbon shift, technofossils, metals in anthropogenic ratios, magnetic soot, and a brief radionuclide tracer. The end Permian is louder than that package in raw impact, but narrower in content. Texture matters too. Industrial civilization leaves low-temperature minerals, cement phases, slags, fly ash glass mixed into sediments. Over deep time they alter, but their shapes and associations stay odd. The end Permian leaves different textures, ash layers, altered volcanic glass, and widespread fine laminations from oxygen-starved muds. It also leaves a biological fingerprint industry cannot imitate directly. The near erasure of many clades, followed by strange, small, disaster-tolerant forms that dominate the early Triassic. Life did not just suffer, it reorganized around heat and scarcity. All of this makes the end Permian a powerful control case. It shows how far nature alone can push the Earth system when a long volcanic pulse injects greenhouse gases, acidifies seas, stresses the ozone layer, and scrambles climate and erosion. It tells us the maximum volume of carbon a planet can move without machines, and the kinds of chemical chords that play when it does. It also tells us what is missing. No technofossils, no industrial halogen signatures in organic matter, no global soot blanket with the magnetic and morphological traits of combustion engines, no synchronized radionuclide blip. Could an ancient civilization have ridden shotgun on that catastrophe, adding its own signal to a volcanic one? If so, the rock record would still be expected to preserve pieces of the technological package in quiet basins and caves. The fact that the end Permian has been cored and analyzed across the world without those pieces turning up argues against that layered scenario. The simplest explanation remains volcanic carbon, ocean stratification, feedbacks, and drawn-out recovery. The lesson for our search is clear. If you discover a thin horizon with a negative carbon-13 plunge that happens almost simultaneously in lakes, shelves, and deep basins, and that horizon carries microplastic ghosts in minerals, combustion fly ash spheres, magnetic soot, unusual industrial halogens in organic matter, and a short-lived radionuclide signal in closed basins, you would not be looking at the end Permian replayed. You would be looking at something new, something that whispers civilization. The Great Dying shows how deafening nature can be. It also shows what even nature's loudest event does not say. With the loudest volcano calibrated, we can tighten the search in time closer to us. The last few million years hold lake beds, peats, cave deposits, and desert dunes with the resolution to capture century-scale jolts. If there was ever a brief, global, technological band before ours, that is where the pages turn fast enough to record it. In the next chapter, we will leave deep time's cataclysms and learn how high-resolution archives write, grain by grain, the story of decades. High-resolution archives bring this search out of myth and into method. In the last few million years, Earth left libraries that turn years into pages. Ice cores, lake varves, peat bogs, cave stalagmites, desert dust beds, and coral skeletons. These do not preserve cathedrals or circuits. They preserve rhythms, ratios, and tiny travelers of air and water. If a brief, global industrial band existed before ours, this is where we would catch it. Varved lakes are the clearest pages. Quiet basins lay down one light dark couplet each year. In millimeter layers you can read floods and summers, pollen shifts as forests reorganize, and soot from distant fires. Varves from the 20th century already store fly ash spheres from coal burning smooth, glassy beads rich in aluminosilicates that drifted from smokestacks and settled like metallic snow. Many cores also show slight jumps in magnetic intensity from engine-made magnetite and shifts in nitrogen isotopes where fertilizer washed downslope. If anything like an industrial pulse brushed the late Pleistocene, varves would be the first to whisper it. A narrow horizon where carbon suddenly lightens, soot spikes, and trace metals step out of their natural mix. Peat bogs write in a different hand. Acidic, anoxic, and slow, they trap airborne metals, organic molecules, and dust, then bury them in waterlogged plant matter. In European peats, lead isotopes trace the rise and fall of Roman and medieval metalworking. In modern layers, nuclear fallout and industrial halogens leave clear markers. Over tens to hundreds of thousands of years, peats compress into lignite and coal. Chemistry changes, but some signals persist. Unusual platinum group ratios from catalysts and odd halogens bound to organic residues. A civilization would not leave plastic bags intact in peat after a few 100,000 years, but it could leave a chemical accent that does not read like volcanoes, sea spray, or lightning. Caves keep quieter books. Stalagmites grow from drip water, banded by seasons and storms. Their calcite tracks trace metals, sulfur and nitrogen isotopes, and even outside fires via black carbon washed in. Some stalagmites preserve century-level resolution across hundreds of thousands of years. They will not hold polymers, but they can carry fingerprints of synthetic organics and lead-mercury patterns that match industry rather than volcanism or dust. Because caves are sheltered, their pages are less smudged by erosion and can align with lake and peat signals to the decade. Ice cores are the most literal time capsules, bubbles of ancient air trapped like tiny ampules. They catch black carbon, lead, nitrate from smog, and even molecules that nature does not make. The catch is survival. Continuous ice rarely lasts beyond about 1 million years, and many stacks are much shorter. A civilization older than the last few glacial cycles would slip out of the ice record, even if it once wrote itself there. But for the late Pleistocene and Holocene, ice becomes the sharpest test. An abrupt global negative swing in carbon-13 across trapped CO2, a short planet-wide soot and nitrate surge, and trace metal ratios that deviate from volcanic recipes. Deserts and winds keep their own ledgers. Loess, thick blankets of wind-blown silt accumulates on the margins of great dust sources. The grains align slightly under Earth's field, giving each layer a magnetic personality. Against that backdrop, engine soot stands out. Polymer fibers and shards lodge between grains. Trace metal ratios shift in ways natural dust does not. Loess sequences can reach close to 1 million years with seasonal to decadal structure, especially in Asia. If a technological episode brushed that window, you would expect a thin horizon with boosted magnetic susceptibility, anomalous rare earth and platinum group patterns, and polymer ghosts locked in clay. Corals grow in bands like calendars. Their aragonite skeletons record temperature, acidity, and trace metal chemistry of seawater, while near-shore colonies fix the heavy metal and organic load flushed from continents. Individual heads rarely outlive a few centuries, but stacked reef terraces preserve generations. A civilization lining late Pleistocene coasts would leave corals with anomalous lead isotopes, whispers of platinum group metals, and thin bands carrying organics not typical of natural sources. How do we turn these shelves into a test? Begin with synchronization. Choose archives on several continents: a mid-latitude varved lake, a high-latitude peat dome, a tropical stalagmite, a Loess plateau, and reef terraces. Date each tightly layer, counting where possible. Radiometric anchors where needed. Then scan for a window no wider than a few centuries where independent proxies pivot together. A global negative swing in carbon-13, paired evidence of warming and acidification, spikes of magnetic soot, trace metal anomalies inconsistent with volcanoes, and, where preservation allows, polymer residues or their metamorphic descendants. If the same narrow layer recurs in lakes, caves, dunes, peats, and corals on different continents, the odds tilt away from local noise. Technofossils are more than plastics. They include shapes and glasses, fly ash spheres with smooth shells and vesicles from high-temperature combustion, titanium-rich micropaints, silica alumina glasses formed in furnaces at temperatures nature rarely sustains at the surface. Polymers crack and carbonize under heat and pressure, but their ghosts can persist as halogen-rich compounds bound into kerogen or as distinctive pyrolysis products when a core sample is gently baked. High-resolution mass spectrometry and microscopy can pick those signals out of natural organic matter. What about radionuclides? The brightest beacons, cesium-137, plutonium-239, and the like, fade on 100,000-year clocks. Yet closed basins can trap their daughters and their glassy carriers much longer. Tiny fallout beads sealed in valves or peat, with xenon or krypton patterns that do not fit lightning or volcanoes, could hold whispers of reactors or tests after the parent isotopes have decayed. Those must be checked against natural analogues such as fulgurites from lightning, volcanic glasses, and impact spherules. There is also the metal ratio test. Natural dust and volcanic ash have characteristic rare earth patterns and platinum group balances. Modern industry taught us to watch for a catalytic triad, platinum, palladium, rhodium, and for neodymium and dysprosium from high-strength magnets. A different civilization might use different alloys, but any culture that reshuffles the periodic table at scale will disturb natural ratios. If you find synchronized, global blips in unusual alloy mixes with no volcanic context and aligned with carbon and soot, curiosity becomes suspicion. The final filter is context. If a suspect band sits inside an ash-rich interval tied to a large igneous province, or lines up with a known impact layer, the natural script deserves top billing. If, instead, it arrives between quiet pages, no flood basalts, no crater, no slow tectonic shift, and yet writes a thin, global, century-scale package of carbon change, soot, metals, and technofossils, you have crossed from interesting to compelling. What would a null result mean? Not that we were certainly first, but that any predecessor stayed quiet enough to evade these libraries. That, too, is a lesson. To pass without a trace, a civilization must live within the planet's slow cycles, move little fossil carbon, keep halogens and metals local, and surrender to entropy gently. The rock record rewards restraint with invisibility. These archives make the search falsifiable. They let us say without myth what should be present if someone like us came and went in the late Pliocene or Pleistocene. Next, we will step deeper, past the reach of ice and valves, and ask how technofossils survive burial and mild metamorphism, how polymer ghosts, alloy ratios, and soot signatures might persist when time presses the pages into stone. When sediments turn to stone, shapes die first, plastics crumble, paper and cloth vanish, steel blooms to rust, and then to oxides that seep into clay. What survives is chemistry and texture, written so small you need microscopes and mass spectrometers to read it. The encouraging twist is that burial and mild metamorphism, hundreds of bars of pressure, and a few hundred degrees of heat do not erase every technological trace. They translate them into forms the rock record can keep. Start with polymers. Sunlight and oxygen snap long chains. Microbes chew the fragments. On beaches and in burn pits, molten plastic welds to sand and cinders into plastiglomerate. Once buried, chains keep breaking until they carbonize, leaving waxy residues and finally soot-like carbon, yet they do not turn into randomness. Microplastics fracture into nanoplastics that cling to mineral surfaces and lodge in pores. Some pieces are captured as inclusions inside, growing crystals, calcite in caves, halite in evaporites, effectively sealed in tiny mineral vaults. Soot is tougher than it looks. Engine exhaust builds tangled stacks of carbon sheets. With pressure and heat, those stacks become more ordered, turning into turbostratic carbon small cousins of graphite that resist chemical attack. Wildfire charcoal does this too. but the chemistry and shapes differ. Industrial soot often arrives as fractal clusters of near-spherical primary particles and can carry embedded magnetite grains from high-temperature combustion. Under a Raman laser or in magnetic scans, those traits separate engine soot from a forest burn. Combustion also leaves glass that stone respects. Coal burning and smelting produce fly ash spheres, hollow beads called cenospheres made of aluminosilicate glass laced with mullite needles, sometimes mantled by magnetite. Volcanic ash and micrometeorites also make spheres, but with different recipes. Cosmic spherules favor iron-nickel and carry high nickel. Volcanic glass mirrors its magma's silica and alkali mix. Fly ash leans aluminum silicon, often with calcium from limestone scrubbers, and it commonly carries trace metal packages tied to fuel and furnaces. Even after burial and alteration, the spherical shells and vesicles can persist as textures. Concrete tries to go home to limestone. In seawalls, rubble, and buried foundations, cement phases hydrate and then carbonate, turning into calcite and silica gels. The precise cement chemistry fades, but it leaves unnatural textures. Angular sand grains glued by micritic calcite, bubble trails from air entraining agents, and cages where ettringite once grew. Steel rebar oxidizes to iron oxides and sulfides that stain pore spaces and seed magnetite. Catalogued together, these low-temperature minerals and textures read like a diary of human masonry long after the mix design is gone. Metals and alloys do not stay shiny, but their ratios endure. Stainless steel corrodes to oxides, copper greens, and then hides in sulfides. Rare earth magnets shed neodymium that binds to phosphates and clays. Yet the periodic table remembers where elements gathered. Road dust carries the catalytic triad, platinum, palladium, rhodium from exhaust systems. Those noble metals are geochemically conservative. They sulfidize or alloy, but they do not evaporate. Buried in peats, lake muds, and deltas, they can build thin horizons with alloy mixes unknown to volcanoes or dust storms. Halogens deserve special attention because they travel with both molecules and metals. Industrial chlorine and bromine do not only arrive as salts, they become part of organic structures, shifting the elemental and isotopic balance of buried carbon. Fluorinated compounds are tougher still. The carbon-fluorine bond is among the strongest in organic chemistry. Per- and polyfluoroalkyl substances, the forever chemicals, resist decay in water and sediments. Heated enough, they defluorinate, but under burial conditions many will persist long enough to be locked into kerogen. The result is a halogen-heavy organic residue that natural kerogens rarely achieve. Radioactivity is the ghost that fades but does not forget. Cesium-137, strontium-90, and plutonium-239 decay on clocks far shorter than geological epochs. Yet fission carves atoms in ways that persist. Xenon and krypton isotopes made in reactors and bombs differ from those made in lightning, volcanoes, or impacts. If those noble gases are trapped in glass beads or sealed pores, their ratios can survive as long as the container does. We even have a proof of concept. At the Oklo Natural Reactor in Gabon, 2-billion-year-old ore-preserved fission products and unusual isotope patterns, evidence that geologic materials can cage nuclear signatures across deep time. Mild metamorphism complicates but can also concentrate signals. At 1 to 200 degrees Celsius, organic matter cooks into more aromatic, condensed forms. Polymers disappear as recognizable chains, but halogen-rich kerogen can remain and release diagnostic compounds when gently heated in the lab. Aluminosilicate glasses recrystallize into mosaics of feldspar, quartz, and mullite, yet spherical shells and vesicles often survive as textures. Magnetite grains coarsen, but keep their magnetic personality. Metals migrate along grain boundaries and into sulfides, locally boosting the very elements industry scattered. Put together, the likely survivors are not museum-ready relics. They are second-language traces, not a bottle. but bubble-rich glass that once was a bottle. Not a circuit, but a platinum-palladium-rhodium cord. Not a shopping bag, but chlorine or fluorine-heavy kerogen tucked between clay sheets. Not a smokestack, but a horizon with fractal soot and a quiet, magnetic whisper. No single clue can stand alone. Volcanic ash can mimic fly ash. Meteor spherules can resemble furnace beads. Wildfires can blacken a page. But volcanoes bring mercury and mantle osmium. Micrometeorites bring nickel and cosmic cobalt. Wildfires bring charcoal without the catalytic metals. When independent lines point the same way, the pattern hardens. There is a sobering corollary. If our own layer is to be quiet in 10 or 100 million years, we would have to avoid writing in these durable inks. Small fossil carbon releases, minimal halogens in organics, little redistribution of noble metals and rare earths, and as little high-temperature glass and soot as possible. The Silurian Hypothesis looks backward, but it doubles as a design brief for any civilization that hopes to pass lightly through stone. With this toolkit of deep-time technofossils, we can now confront the forgeries. What natural processes most convincingly counterfeit industrial signals, and how do we catch them under the microscope and in the mass spectrometer? That is our next step, because good detectives learn a forger's tricks before they trust a signature. Forgery is the planet's favorite hobby. It can stamp out glassy spheres without furnaces, scatter metals without smelters, blacken the sky without engines, and even alter isotopes without reactors. If we are going to treat technofossils as evidence, we have to learn the forger's moves and the tests that expose them. Start with spheres, because they are deceptively persuasive. Industrial fly ash from coal and heavy oil yields smooth, often hollow cenospheres of aluminosilicate glass, sometimes rimmed with magnetite and spiked with mullite needle-like crystals grown in furnace conditions. Nature can also make spheres. Meteor ablation rains down micrometeorites rich in iron and nickel. Impacts melt crust into glassy spherules called microtektites. Volcanoes quench ash into shards and droplets. The separations are in recipe and texture. Micrometeorites carry high nickel, often metal cores, and cosmic chromium-cobalt ratios. Impact spherules show volatile loss patterns and shocked mineral inclusions. Volcanic glass mirrors magma chemistries and lacks the mullite that screams boiler. Under the microscope, cenospheres have telltale hollow vesicles and composition clusters centered on aluminum silicon with calcium from flue gas scrubbers. Pair morphology with geochemistry, and most spheres confess their origin. Soot is another master imitator. Forests and peatlands have burned for hundreds of millions of years, and fires write black carbon into nearly every archive. Industrial soot overlaps that signal, but differs in structure and hitchhikers. Engine soot forms fractal aggregates of near-spherical nanocarbon primaries, and frequently co-travels with magnetite, vanadium from heavy oil, and the catalytic triad platinum, palladium, rhodium from exhaust systems. Wildfire charcoal is more plant-like in texture, with cellular ghosts and a broader spectrum of polycyclic aromatic hydrocarbons. Raman spectroscopy, magnetic coercivity, and trace metal ratios can draw the boundary. A global, nearly synchronous spike of fractal soot with traffic metals is hard to fake with lightning and logs. Lightning itself forges glass. Fulgurites fuse sand into wormy tubes and trap peculiar nitrogen oxides. Shock chemistry can yield odd xenon and krypton mixes, but fulgurites are local and chaotic. They do not settle as worldwide millimeter-thick sheets synchronized to the decade. A civilization-scale soot horizon would be thin, global, and time-locked across lakes, loess, peats, corals, and caves. Fulgurites carve isolated signatures that vanish a short walk away. Impacts are famous for metal tricks. The end Cretaceous layer blooms with iridium and platinum group elements and carries glassy spherules and shocked quartz. Big impacts also shake osmium isotopes toward extraterrestrial values. Could an impact counterfeit an industrial package? Only in part. It would not deliver plastics or polymer ghosts. It would come with a crater, a gravity anomaly, and a ballistic blanket. Its metals would skew toward chondritic patterns, not catalytic ratios or rare earth mixes tied to magnets and batteries. If you see platinum without iridium, platinum with palladium and rhodium in traffic proportions, and neodymium dysprosium offsets that track human alloying, you are not reading a meteor page. Volcanoes write long, layered forgeries. Large, igneous provinces lace sediments with ash, mercury spikes, and mantle-leaning osmium. Magma intruding organic rocks bakes them into thermogenic CO2 and methane. On black shales, anoxic chemistry concentrates molybdenum and vanadium, metals that also show up in some industrial settings. The countertest is context and pace. Volcanic bands spread over thousands of years and tie to recognizable provinces. Industrial bands would sharpen into centuries and lack a rift's ash ladder. Volcanism does not mass-produce smooth aluminosilicate cenospheres with mullite needles, nor does it sprinkle the catalytic triad in roadside ratios worldwide. Hydrothermal systems blur the line in metal space. Vents and basins can enrich copper, zinc, arsenic, and even platinum group elements in ways that look industrial. But their fingerprints cluster spatially, hug faults and basins, and carry sulfur and iron signatures that betray hot water. Industry is aerial. It smears metals across continents with prevailing winds and rivers. A thin, simultaneous horizon of platinum, palladium, rhodium on 3 continents argues for tailpipes, not a dozen coincident vents. Halogens tempt confusion too. Sea spray writes chlorine and bromine into coastal peats and lake beds. Volcanoes loft HCl and HBr. Salt flats trap halogen-rich minerals. Industry, however, builds the halogens into carbon chains. Fluorinated organics and chlorinated solvents leave residues with elemental and isotopic footprints, unlike sea salt or volcanic acid. Bound halogens in kerogen, anomalous chlorine 37 to chlorine 35 ratios tied to synthesis routes, and pyrolysis products that match known industrial families, separate factory ghosts from ocean breath. Radioactivity seems like a trump card, but decay is relentless. The forgeries here are lightning in sand, which can create neutron bursts and rare isotopes, and natural reactors such as Oklo, which altered uranium and preserved fission patterns for billions of years. The counters are geometry and gas. Industrial fallout arrives as a global dusting with characteristic size distributions, and, crucially, noble gas isotopes in sealed beads that match reactor spectra, not lightning's flash. Natural reactors require concentrated ore bodies and leave mineralogical renovations in place. A civilization's pulse would be thin, widespread, and decoupled from uranium mines. Diagenesis chemistry during burial can turn honest signals crooked. Metals migrate along grain boundaries. Organic molecules dechlorinate. Glasses recrystallize. Magnetite coarsens. A forged technofossil can seem to appear where none was laid. The defense is redundancy across proxies and archives. If a suspect metal ratio shows up only where groundwater flowed, but the carbon isotope, soot, and polymer ghosts do not match, you are seeing post-burial editing. If the same narrow layer repeats across a cave, a lake, a peat dome, a Loess plateau, and a reef terrace with aligned timing, diagenesis cannot plausibly conjure that orchestra everywhere at once. Sampling bias can also masquerade as mystery. High-energy environments erase thin layers. Quiet basins overrepresent local industry. The cure is a networked approach. Multiple continents, multiple depositional settings, tight dating, and blind analyses where labs do not know which layers are suspect. Pre-registered criteria deciding in advance which thresholds would trigger an industrial classification guard against wishful thinking. The Silurian Hypothesis only stays scientific if it risks being wrong in public. A final forgery is us our preconceptions. Humans pattern seek. We see faces in clouds and industry in black shales. The antidote is to practice on known cases. Give teams cores that include the 20th century, mixed with natural analogues like the Paleocene Eocene Thermal Maximum and Oceanic anoxic events. Ask them, using only pre-registered tests, to flag the industrial horizon. If they consistently find our century and consistently acquit PETM and OAE-like layers, the toolkit earns trust. If they do not, recalibrate before reading deeper time when the forger's catalogue is laid out. Impacts, volcanoes, fires, lightning, hydrothermal basins, diagenesis, the remaining territory for a false positive shrinks. What survives as a credible industrial signature is a package. A rapid, global carbon-13 decline, thin, synchronous soot and nitrate boosts, technofossils such as xenospheres with mullite or polymer ghosts in minerals, catalytic and rare earth metal anomalies in airborne patterns, sealed noble gases with reactor-like isotopes in microglass, and the absence of volcanic impact or hydrothermal context. That package is not impossible for nature to mimic in pieces. It is vanishingly hard for nature to assemble in full. Armed with these filters, we can turn from method back to clues. Scattered reports already hint at oddities, layers with unexpected metal mixes, beaches welded into plastiglomerate, peats that hoard 20th century catalysts with astonishing fidelity. Those are our calibration points. To hunt deeper, we need candidate windows in time where a brief, global, unnatural band could hide. The late Pliocene warm spells, the mid-Pleistocene climate transition, and enigmatic hiatuses and unconformities in continental records are prime places to look next. Time windows matter. If a civilization-length event ever happened before us, it would be a blink in geological time, a few centuries to a few millennia. To catch a blink, you don't stare at the whole night sky. You watch places where the camera was already rolling fast. 3 chapters in Earth's recent past give us our best chance. The warm Pliocene, the great rhythm shift of the mid-Pleistocene, and the abrupt cold snap called the Younger Dryas. Begin with the mid-Pliocene warm period, roughly 3.3 to 3 million years ago. Sea level stood higher. Global temperatures were a few degrees warmer than now. Forests and grasslands occupied different maps. Crucially, there was no giant volcanic province exploding at that exact time, no fresh crater driving the climate. The warmth seems to have been sustained by steady, natural carbon levels and long, slow feedbacks. That makes the Pliocene a clean background. If a thin, century-scale disturbance had been superimposed on that stable plateau, a sudden global dip in carbon-13, a spike of magnetic soot, an odd alloy mix, it would stand out like a scratch on polished glass. Where do we read the Pliocene at high resolution? Siberia holds a gift. Lake El-Jijijin, a deep, undisturbed crater lake with sediments that stretch back 3.5 million years. In a core from such a lake, you can track season-to-season changes in grain size, pollen, soot, and trace metals. Pair that with ocean drift deposits downwind of continents, natural dust collectors that preserve airborne particles, and with long low-S stacks in Asia that capture wind history grain by grain. If a civilization left a global fingerprint during a Pliocene century, these archives would be the first to whisper it. The test is simple and strict. Look for a narrow horizon repeated across basins on different continents, where carbon lightens, soot and nitrates jump, and catalytic or rare earth metals deviate from volcanic and aeolian recipes. If the Pliocene stays smooth under that lens, we mark it quiet. Next comes the mid-Pleistocene transition, between about 1, 2 million and 0.8 million years ago, when Earth's ice age rhythm changed key. Before the transition, ice sheets waxed and waned mostly on a 41,000-year beat, linked to the tilt of Earth's axis. Afterward, the system locked into longer, roughly 100,000-year cycles, with deeper freezes and more dramatic thaws. Many mechanisms have been proposed changes in ice sheet mechanics, the slow stripping of soils by repeated glaciations, tweaks to the carbon cycle, but none involve factories. The point for us is that the MPT is global, well sampled, and messy in a productive way. Chinese loess sequences, North Atlantic dust records, Mediterranean sapropels, and cave stalagmites from many latitudes capture the transition at decadal to centennial scales. That makes the MPT a stress test for our toolkit. Can we walk through thousands of pages where climate is shifting for natural reasons and not once be fooled into calling an industrial band? We should expect to see dust change, pollen shuffle, and oxygen isotope swings that track ice volume. We should not see a synchronized thin package of negative carbon-13, magnetic engine soot, polymer ghosts in minerals, and catalytic metals on 3 continents at once. If we do, the burden of proof shifts to the extraordinary. If we do not, and so far, in published high-resolution records, we do not, the MPT becomes another calibration that narrows the space for false positives. Then there is the Younger Dryas, the sudden chill that interrupted the end of the last ice age about 12,900 years ago and ended around 11,700 years ago. Here the resolution is exquisite: Greenland and Antarctic ice cores with annual layers, valved lakes in Europe and North America, cave formations that grew band by band. The onset is fast. The climate whip soared in decades. Some studies report platinum anomalies, nanodiamonds, and microspheres near the onset. Others do not, and the impact trigger idea remains hotly debated. That controversy is exactly why the Younger Dryas is useful to us. It is a superb proving ground for the forgery file. If a global impact or meltwater reorganization can produce metallic spherules or odd dust without any technofossils, our methods must acquit the natural event. The industrial package must remain a package: carbon, soot, metals in anthropogenic ratios, polymer or halogen clues, and the absence of an impact's unmistakable context, or we are just chasing glitter. Beyond these headline chapters are quieter alleys where evidence hides. Continental records are full of hiatuses and unconformities, pages missing, pages glued together, pages smeared. Sometimes the gaps are erosional. Sometimes a lake dried out or a river leapt its banks. A civilization-length event could nestle against such a gap where sediment briefly piled fast, then paused. That is why edge environments are important. Lake margins where storms dump thin, sortable layers, sheltered caves where dripstones catch airborne dust, coastal marshes that rise with sea level and archive metal and soot as they go. The rule is repetition. A single odd layer in one basin is an anecdote. The same layer, within dating uncertainty, in 3 basins on 2 continents is a signal. What about the ocean? Our largest archive. Deep-sea sediments accumulate slowly, but continental shelves and margins can stack centimeters per century. There, laminated muds hold industrial-style signals from the 20th century: fly ash spheres, magnetic soot, fertilizer-driven nitrogen shifts carry that logic backward. On shelves where sediments of Pliocene or early Pleistocene age are accessible, we can core for thin anomalies. The trick is diagenesis. We must guard against metals and halogens that moved after burial. That means pairing geochemistry with textures under the microscope: cenospheres with mullite needles, soot fractals with engine-like magnetite, bubble-rich aluminosilicate glass that does not match the local ash. If chemistry says odd, but textures say volcanic, a practical search plan emerges. Choose 5 flagship targets: a high-latitude lake with million-year pages, a mid-latitude loess plateau, a coastal peat dome, a tropical cave, and a continental shelf core. Pre-register the criteria that would trigger an industrial call. Run blind splits through multiple labs so analysts do not know which layers are suspected. Track carbon-13 and oxygen-18. Count cenospheres and soot morphologies. Scan for platinum, palladium, rhodium triads and rare earth patterns. Test for halogen-heavy kerogen. And, where glass beads allow, measure noble gas isotopes for reactor-like fingerprints. Then stitch the timelines together and ask one question: does any century-scale horizon reappear across archives with the same package? If the answer is no, The Silurian Hypothesis does not die, it matures. We would have learned where a predecessor could not hide, not in the last million years, not in the Paleocene's calm, not inside the MPT's noise, not beneath the younger Dryas's microscope. A civilization could still lurk deeper in time, where pages are thicker and the camera was slower, or it could have lived lightly, writing in inks that stone does not keep. Either way, a null result is still a map. It tells us which doors we have already opened. If the answer is yes, if we find the package, then caution grows, not certainty. Nature forges clever counterfeits. We would recheck context for ash ladders, craters, and hydrothermal seams. We would test fresh sites, add more continents, and invite critics to try to break the case. The goal is not a headline. The goal is a layer that survives every attempt to explain it away with volcanoes, ice, or impacts. Only then would we whisper, not shout. Someone like us might have passed this way before. The fossil record is not a book. It is a jigsaw puzzle missing most of its pieces. When we talk about gaps, we are often seeing how the archive is built, not necessarily how life actually lived. To judge whether an earlier civilization could vanish, we need to understand why the record of ordinary biology looks so ragged in the first place, and how rocks can erase whole chapters without leaving a margin note. Start with a simple truth. Most organisms never fossilize. To make a fossil, you need the right death in the right place, under the right chemistry, followed by burial before scavengers and oxygen do their work. Hard parts help, but even shells dissolve in acidic waters, and bones crumble if burial is slow. Sandbars migrate, rivers jump, banks, coastlines march back and forth. The result is what paleontologists call preservation bias. Wetlands and quiet lake floors keep secrets. Mountain slopes and uplands do not. If a species lives mostly in places that do not write, its story is told by rumors and rare cameos. Now add time's statistical trickery. The Signor Lips effect says that even a sudden extinction looks slow in the rock record because the last fossil you find is almost never the true last survivor. Imagine flipping a coin and writing down only every 10th coin toss. Your plot of heads and tails will look streaky, even if the real sequence ended abruptly. The same logic makes the first appearance of a group seem too late. Ghost lineages show up when anatomy says two lineages must have split by a certain date, but the earliest fossils we've found are younger. The missing time is a gap in discovery and preservation, not necessarily a gap in life. Consider named gaps that haunt textbooks. Romer's Gap in the early Carboniferous spans tens of millions of years with precious few fossils of land vertebrates. For decades, it looked like a biological lull. Then, in the right rocks in Scotland and Nova Scotia, researchers found rich sites that started to fill it. The animals were there. The rocks had simply been stingy. The Cambrian explosion looks like a sudden appearance of complex life, because Ediacaran ecosystems rarely preserved hard parts. As shells and burrowing spread, preservation improved and the record blossomed. Apparent leaps in complexity reflect, in part, leaps in the rock's willingness to keep notes. The land itself edits. Unconformities surfaces where younger rocks rest directly on much older ones are erasures. The most famous is the Great Unconformity, where Cambrian sandstones sit on basement rocks more than 1 billion years older in places like the Grand Canyon. Everything that happened between those ages, on that surface, is gone at that spot, planed off by uplift and weathering, likely aided by the scouring of snowball Earth glaciers. Multiply that kind of editing across continents and you see how entire landscapes can be lifted, stripped, and recycled before new sediments arrive to start fresh pages. Coasts, where civilizations love to live, are especially ruthless editors. Shorelines march with sea level, deltas grow, drown, and migrate. Storms tear up floodplains and dump their cargo elsewhere. The continental shelf, a natural city shelf, is frequently reworked and commonly lost to subduction or buried under later sediments that do not preserve fine detail. If a technological species favored river mouths and lowlands as we do, Most of its built environment would be written on palimpsests that are constantly being scraped and re-inked. Even the bones of billions of large animals leave a whisper. Take the Pleistocene megafauna. Mammoths, giant ground sloths, saber-toothed cats, iconic, widespread, and recent, are known from a few rich sites and a scatter of finds, not from continuous layers of carcasses. The denominator, how many individuals lived and died, is enormous. The numerator, how many fell into tar pits, caves, or oxygen-poor lake bottoms, is tiny. If that is the signal for charismatic megabeasts across continents within the last 50,000 years, scale your expectations for a brief, urban species tucked into erodible coasts millions of years ago. What about the human layer itself? Ironically, much of what we build sits in places that do sometimes preserve landfills, estuaries, and floodplains. Landfills are anoxic chemical factories. They trap metals, halogen-rich organics, and microplastics that can be buried and sealed. Yet even here, time favors chemistry over form. Bottles become glass shards in clay, concrete mineralizes, plastics crack and carbonize, metals migrate into sulfides. The technofossils, likeliest to survive deep time, are not statues or circuits but ratios and residues. Catalytic platinum group spikes, polymer ghosts bound into kerogen, soot with engine-like magnetism. Aluminosilicate cenospheres. If you are looking for skyscrapers, you are looking for the wrong kind of evidence. This is why the Silurian Hypothesis focuses on the global, the thin, and the synchronous. A civilization writes a narrow band everywhere at once because it rearranges carbon and elements faster than rivers and wind can. The fossil record's gaps do not defeat that search, they refine it. We do not need perfect continuity to see a global negative swing in carbon-13, paired with soot, halogens in organics, and catalytic metals. We need a few well-dated high-resolution shelves on different continents that overlap in time. If those pages are quiet, then either there was no prior civilization in that window, or it lived in a way that did not disturb those particular inks. There is another kind of gap that tempts storytellers. Hiatuses that line up with culture in our own Holocene. In many regions, the archaeological record shows rises and falls, cities blooming and failing, while nearby lake or cave records register climate jolts. It is natural to project that rhythm into deeper time and imagine earlier cycles. But archaeology works on scales where artifacts persist. Geology in deep time does not. A brief, scattered network of toolmakers with small fires and local metals would be invisible a million years later. A planetary heat engine run for centuries would not be. The distinction matters. The Silurian Hypothesis is not a hunt for Paleolithic Romans. It is a test for planetary scale industry. A final subtlety, the pull of the recent. Younger rocks are more common at the surface, less buried and less metamorphosed. So we find more young fossils and artifacts, simply because the library shelves are easier to reach. Deep time has fewer books on display. That means our failure to see a prior civilization farther back is partly a function of access. The remedy is not hand-waving, it is targeted exploration, drilling in old quiet basins, reanalyzing existing cores with new instruments, and pre-registering criteria, so a positive result is not just in the eye of the beholder. All of this makes the fossil record's silence more meaningful, not less. The gaps are expected for bones, bricks, and tools. They are not expected for a global chemical package delivered in a few centuries. If that package is absent in the Pliocene and Pleistocene's best pages, the burden shifts toward either no predecessors or very quiet predecessors. If we ever do find such a package, it will not be in a museum case labeled with statues. It will be a thin, stubborn line in mud and cavestone, the kind of clue only a planet can keep. With the logic of gaps in mind, we can return to the provocative idea that opened our story: glassy spheres and rare metal anomalies scattered through ancient layers. What looks nuclear? What looks like impacts or industry? In the next chapter, we will pick apart spherules, platinum spikes, and the strange glasses that both factories and asteroids can make, and learn how a geochemical accent can distinguish a bomb from a bolide. If you want to tell a bomb from a bolide, start with the glass. Impacts make tektites, natural glass droplets, launched into ballistic arcs that can rain across continents as strewn fields. With a strong silica bias and the presence of lecitellurite, a high-temperature form of silica that forms only in extreme shock. You often see shocked quartz with neat parallel planar deformation features and high-pressure minerals like coesite or stishovite nearby. The platinum group elements tilt toward a chondritic pattern. Osmium isotopes nudge toward an extraterrestrial mix, and the iridium spike at the Cretaceous-Paleogene boundary remains the poster child for an impact signature. An impact horizon is a loud, short chapter with a crater somewhere on the map, a blanket of spherules and geochemistry that points to space. Industrial furnaces and power plants also make spheres, but their spheres speak a different dialect. Coal combustion yields fly ash cenospheres smooth, often hollow aluminosilicate beads sometimes studded with mullite needles, a crystalline phase grown at furnace temperatures and rare in natural surface processes. Magnetite skins and vesicle patterns tell you the droplets floated in hot, oxidizing gases rather than blasted through vacuum and re-entry. The alloy story is different too. Instead of chondritic iridium, you find traffic metals, platinum, palladium, rhodium in ratios familiar from catalytic converters, paired with vanadium and nickel, where heavy oils burned. If you ever found a thin global layer rich in mullite-bearing cenospheres and the catalytic triad without the telltale iridium of an impact, you would not be reading an asteroid page. Volcanoes complicate the picture with ash and mercury, but their glass mirrors magma families basaltic, andesitic, rhyolitic rather than the lime-boosted, aluminum-rich glasses born in boilers and kilns. Volcanic horizons stack over thousands of years and tie to known provinces and ash ladders. They do not produce the worldwide, nearly synchronous sprinkling of platinum, palladium, rhodium we measure downwind of modern cities. And they do not sprinkle cenospheres with mullite needles across quiet lake bottoms on 3 continents in the same decade. Now turn to nuclear glass. Ground-burst weapons fuse soils into vitrified sheets. At Trinity, desert sand mixed with test site metals to form bottle-green trinitite. Under a microscope, trinitite hosts bubbles, metal splatters, and embedded fragments from tower wiring and bomb components. Its most decisive accent is isotopic. Fission products like cesium-137 and strontium-90 at first. Then, as centuries tick by, daughter isotopes and noble gases with fission-biased ratios sealed in the glass. Many radioisotopes decay too fast to cross deep time, but some tracer parents are long-lived. Uranium-236 half-life, 23 million years, forms when reactors or bombs shower natural uranium with neutrons. Iodine-129, half-life, 15.7 million years. And technetium-99, 211, 0 years, can also persist if they are trapped in closed microenvironments. Chlorine-36, 301, 0 years, has been mapped from 20th century tests in snow and groundwater. Even if plutonium-239, 24, 0 years, and plutonium-240, 600 years, fade, excess 236U or 129I lodged in glass beads, or reactor-like xenon and krypton isotope patterns sealed in vesicles, could survive long enough to be read millions of years later. Impacts and volcanoes do not make those isotope constellations. Distribution matters. Impact spherules thicken near the crater and thin in a ring that respects wind and ballistic physics. Tektite-strewn fields are vast but coherent, tied to a single event. Industrial fallout is aerial and repeated. It smears thin, synchronized horizons into lakes, peats, loess, and cave stones worldwide within years. Nuclear test debris behaves similarly, global but time-locked to a narrow interval. If you see a single thin layer with reactor-like noble gases in microglass repeated on multiple continents and dated within a century, you are listening to machines. Platinum spikes deserve special caution because they can come from more than one story. Cosmic dust rains platinum group elements continuously. Big impacts bring iridium-rich jolts. Volcanoes contribute little. Cities in the catalytic converter era emit platinum, palladium, and rhodium in human ratios. The way out is to read the chord, not a single note. A chondritic impact package carries iridium with the rest and pairs with shocked minerals. An anthropogenic package arrives with a negative carbon-13 swing, magnetic engine soot, xenospheres, and urban-style PD, RH. A volcanic interval brings mercury surges, mantle-leaning osmium, and ash layers, but little PGE. In short, add context, mix of metals, and mineral textures, until only one melody still fits. Odd glasses show the same pattern of discrimination. Fulgurites, glass tubes forged by lightning and sand trap, nitrogen oxides, and sometimes exotic noble gases. But they are rooted and local. They do not appear as a millimeter-thick film that repeats across lakes and caves on 2 continents in the same decade. Obsidian is volcanic. Its chemistry plots neatly with magmatic families. Slag from smelters, by contrast, is a calcium aluminosilicate brew with entrained metal droplets and factory temperature minerals. In section, it can look like a man-made breccia, angular clasts glued by micritic carbonate from cement carbonation. In deep time, many of those phases recrystallize, but the associations remain odd. Mullite needles in old lake mud, aluminosilicate xenospheres welded into clays, and micromagnetite bound to soot fractals where no ashfall is mapped. There is also the daughter test. Even when prime evidence decays, what it becomes can still point backward. Plutonium decays by alpha emission to uranium. A pulse of 239 pu would leave a whisper of 235 UXS against background in a sealed microdomain. Chlorinated solvents and fluorinated organics decompose and defluorinate under burial, but they leave halogen-heavy kerogen and distinctive pyrolysis products when heated in the lab. Polymers crack into shorter chains and aromatics, yet nanoplastics cling to mineral surfaces and can become inclusions inside growing crystals. None of those are museum pieces. All are readable if you know to ask. If we apply this toolkit to famous natural layers, the stories separate cleanly. The KPG boundary shouts impact, global spherules, shocked quartz, iridium spike, osmium tilt, a crater at Chicxulub, and no technofossils. The Australasian tektite field around 0.8 million years ago paints Southeast Asia with shock glass but brings no catalytic metals, no soot package, no halogen-rich organics. Large igneous provinces lace their intervals with ash beds, mercury, and osmium that leans mantle, and build black shales by anoxia rather than by factories. Modern sediments, in contrast, already archive our century as a wafer-thin but unmistakable band of fly ash, magnetic soot, catalytic PGEs, negative carbon-13, fertilizer-tilted nitrogen, and a brief radionuclide dusting. What, then, would count as a nuclear industrial horizon in deep time? A globally repeated sub-century layer that combines a sharp negative carbon-13 dip, thin soot and nitrate boosts, xenospheres with mullite and magnetite skins, anomalous PTRH without iridium, halogen-heavy organic residues, or their metamorphic descendants, and sealed noble gases in microglass, with reactor-like isotope patterns arriving without a mapped crater, without an ash ladder tied to a volcanic province, and without hydrothermal metal zoning. That package is overkill, and that is the point. Nature can fake pieces. It rarely stages the whole play. Of course, the planet edits. Glass devitrifies. Metals migrate. Diagenesis smears signals. That is why the search leans on replication across archives and continents, on blind analyses, and on pre-registered criteria. If 3 or more well-dated sites carry the same thin layer with the same package, and if every natural forgery file is exhausted, we would not claim certainty. We would claim a hypothesis strong enough to beat serious attempts to break it. With glass, metals, isotopes, and textures sorted, we can step back to the idea that began our journey. Thin lines and scattered spheres in ancient muds that seem to echo modern industry. Are they the planet's own handiwork, industry's distant mirror, or just our eyes chasing patterns? In the next chapter, we will assemble a handful of real case studies, enigmatic metal mixes, odd spheral beds, abrupt isotope wiggles, and walk them through the tests, letting the rocks argue for themselves. Case studies are where the Silurian hypothesis stops being a parlor thought and learns to argue with rocks. To keep the test honest, we'll choose examples that have tempted researchers toward extraordinary explanations and walk them through our filters: composition, texture, timing, distribution, and context. Start with the much-debated onset of the Younger Dryas. In several ice and lake records, scientists reported platinum enrichments and beds of tiny spherules close to the decade when climate snapped cold. One reading says, cometary dusting. The skeptical reading says, fires, wind sorting, or small regional eruptions can nudge platinum without any crater. Now apply the full package test. The platinum does not arrive with the catalytic triad platinum, palladium, rhodium in tailpipe ratios. The spherules are mixed. Many are iron-rich or silicate glass, without the smooth, often hollow, aluminosilicate cenospheres that coal furnaces mass produce. There is no layer of magnetic engine soot synchronized across continents, no polymer ghosts in minerals, no reactor-like noble gases sealed in microglass. Distribution is patchy rather than nearly simultaneous in multiple archive types. Verdict: interesting natural signal, not an industrial band. Next, the Australasian tektite event, roughly 800,000 years ago. Southeast Asia and the downwind Indian and Pacific Oceans, where a storm of shock glass so abundant that drill cores count microtektites by the thousands. Chemistry plots along silica-rich lines tied to target rocks, and lesser tellurite, the ultra-high temperature silica, haunts the shards. Shocked quartz shows up where it should. Platinum group elements tilt toward a chondritic balance. Osmium leans extraterrestrial. Crucially, there is no catalytic converter fingerprint, no fly ash cenospheres with mullite needles, no industrial halogen residues bound into organic matter. Distribution matches a classic tektite-strewn field thick near the source, thinning predictably with distance, not a thin, nearly synchronous global dusting. Verdict: impact glass, not industry. Third, glassy particles reported at the Permian-Triassic boundary in parts of South China. Spheres showing up in the world's worst extinction will raise eyebrows. Under the microscope, though, many grains prove to be altered volcanic glass or devitrified ash shards, mercury spikes, and osmium isotopes lean volcanic. Timing aligns with pulses from the Siberian traps. Where spheres occur, they lack the aluminosilicate chemistry and mullite needles, typical of high-temperature boiler ash, and they do not co-travel with catalytic metals or a narrow band of magnetic soot. The broader package black, laminated muds rich in pyrite framboids, biomarkers of euxinia. Carbonate loss from acidified seas fits a long volcanic greenhouse, not a century-scale industrial burst. Verdict: volcanism and feedbacks, not machines. Now flip the lens to a case that tempts the other way. 20th century layers in lakes, peats, loess, caves, and shelf muds. Here, the industrial package is as clear as a billboard. Carbon-13 drops in trapped CO2, nitrates, and black carbon spike. Magnetic susceptibility jumps from engine-made magnetite. Smooth aluminosilicate cenospheres with magnetite skins settle into varves. Platinum, palladium, rhodium ratios match traffic. Microplastics and their weathered cousins bind to clays. And for a mid-century moment, a radionuclide dusting appears in closed basins. In a few sites, noble gases sealed in tiny glass bubbles carry fission-biased isotope patterns. Distribution is exactly what the hypothesis predicts: a wafer-thin, near-synchronous horizon repeated across different archive types on different continents. Verdict: this is what civilization looks like in stone. Fifth, rumored Pliocene oddities, reports of alloy mixes and carbon wiggles in scattered cores. On close inspection, the alloys tend to be hydrothermal overprints or diagenetic concentrations where groundwater moved metals along fractures. Rare earth patterns look like hot water systems, not factories. Platinum group elements, when elevated, lack the anthropogenic triad's tight ratios and instead echo dust, rivers, or micrometeor rain. The carbon wiggles resolve to droughts, fires, or local productivity swings. No technofossils, no soot package, no synchronized timing across archives. Verdict: natural noise in a slow, warm world. Sixth, the impact-looking spike at the Cretaceous-Paleogene boundary are best control against metal false positives. Iridium and osmium scream chondritic. Shocked quartz is universal. Spherals blanket the globe, and a crater sits at Chicxulub. Yet there is no catalytic metal trio, no fly ash spheres with mullite, no polymer ghosts, no reactor-like noble gases. It is the perfect reminder that a huge metal anomaly can coexist with zero technofossils. Verdict: cosmic, not civic. Seventh, a preservation lesson from Holocene, river terraces, and deltas. Archaeologists sometimes find calcium aluminosilicate slags within trained metal droplets and angular clasts, then watch those phases alter toward carbonates and clays within a few millennia. The chemistry drifts, but the textures persist. Bubble trails, quenched rinds, odd glass-to-mineral mosaics. Scale that process to deep time, and you understand why low-temperature technofossils we should expect mullite-bearing cenospheres, soot fractals with engine-like magnetism, halogen-heavy kerogen. Catalytic PGE horizons would survive as textures, ratios, and residues even after their freshest forms are gone. These cases do more than separate suspects. They teach tempo. Impacts write seconds to years. Volcanoes write thousands of years. Industry writes decades to centuries. The rock record translates everything into thickness and grain size. Place candidate layers on that tempo chart, and most natural events spread too thick and too slow to mimic a civilization's global, paper-thin band. The exceptions, the impact layers, carry unmistakable props: shocked minerals, chondritic metals, a crater. They also teach distribution. Impacts obey ballistic physics. Debris thins with distance in predictable rings. Volcanoes obey wind roses and eruptive phases. Hydrothermal systems hug faults and basins. Only industry and nuclear tests manage the odd trick of near-simultaneous dusting across lakes, caves, peats, dunes, reefs, and shelves on multiple continents. That is why repetition across archive types is our strongest lever against being fooled. And they teach humility. Each time an odd metal ratio or a shiny bead appears in an old core, the imagination leaps. The discipline is to ask for the whole package and invite every natural forgery to take its best shot. When the forgery file wins, we learn. When it loses, when a thin layer quietly checks every box while dodging craters and ash ladders we do not celebrate, we replicate. If a prior civilization wrote itself into stone, these are the tests it must pass and the contexts it must avoid. So far, Deep Time's best resolved chapters show nature's handwriting, not a stranger's. But the search is young, and the instrument shelf grows richer each year. Next, we'll widen the lens from case files to strategy, where to drill, what to measure first, and how to design a global project that could, within a decade, rule most of the late Neogene either in or out. A real search needs a plan, not a mood. If we want to rule most of the late Neogene in or out for a prior industrial band, we can design a project that treats Earth like a network of synchronized laboratories. The aim is simple and strict. Look for a thin, globally repeated horizon that carries the full package: carbon-13, going light, soot and nitrates, technofossils, catalytic metals, halogen-heavy organics, and, where possible, reactor-like noble gases in sealed microglass, arriving without the ash ladders of a volcanic province or the debris of an impact. Start with the archives that write fast. Choose 5 flagship settings spread across latitudes and climates so that no regional quirk dominates the verdict. 1. A high-latitude, deep, undisturbed lake with million-year pages, the kind that settles varves and traps airborne dust with minimal stirring. 2. A mid-latitude loess plateau, built grain by seasonal winds, storing magnetic personalities and airborne metals. 3. A coastal peat dome whose anoxic layers sip atmosphere and rain for centuries at a time, hoarding trace elements and organics. 4. A tropical cave where stalagmites grow from drip water, banded by seasons and storms, locking in isotopes and trace metals. 5. A continental shelf mud core from a margin that accumulates centimeters per century, fast enough to catch a brief episode in high resolution without the blurring of the abyssal deep. Next, the instruments. Read carbon with stable isotope mass spectrometers that chart D-double-C in bulk carbonates and organics, and pair it with D-double-Senken and D-double-Senke-Porter-S to fingerprint fertilizer-like nutrient cascades and anoxia. Scan for technofossils with scanning electron microscopy and energy-dispersive X-ray spectroscopy. Cenospheres show hollow shells, magnetite skins, and mullite needles that furnaces coax but volcanoes rarely do. Use Raman spectroscopy to tell engine soot's fractal aggregates from wildfire, charcoal's plant ghosts. Pull trace metals with inductively coupled plasma mass spectrometry, and watch for the catalytic triad, platinum, palladium, rhodium in tailpipe ratios, plus rare earth patterns tied to magnet alloys. Probe halogen-heavy organic residues with pyrolysis GCMS and high-resolution mass spectrometry. Fluorinated and chlorinated families leave families of fragments that sea spray and volcanoes do not. Where microglass is present, crack vesicles and measure xenon and krypton isotopes on noble gas machines tuned to separate reactor spectra from lightning and impacts. Map textures with micro-CT and thin sections, so chemistry never floats free of context. Dating is where confidence lives. In varved lakes, count bands and cross-check with radiocarbon anchors. In caves, use uranium-thorium dating on stalagmite layers. In lows, combine luminescence dating for dust with magnetic stratigraphy. In peats and shelf muds, layer counts and tephra markers tie to regional volcanic timelines, even when we are not chasing volcanoes as causes. Then stitch all the age models together with Bayesian chronology software so the uncertainties are explicit, and so that a synchronous call means within decades to a century across continents, not hand-waved simultaneity. Guard the search against wishful thinking. Pre-register the criteria that would trigger an industrial flag before a single core is opened. The minimum size of a D-diamond to Gabe-C drop, and the maximum time allowed for its onset. The counts and morphologies of cenospheres per gram required to call a fly ash horizon. The thresholds for peat roach ratios that drift beyond volcanic and dust backgrounds. The Raman and magnetic signatures that separate engine soot from charcoal. The halogen fragment families that clear the bar for industrial organics. The noble gas isotope windows that match reactor yields. Then, run blind splits to multiple labs so analysts do not know which depths are suspected. Contamination is a saboteur. Modern plastics shed from lab coats and filters. Urban dust brings the same metals we seek. The protocol needs pre-baked glassware, clean air hoods, cotton rather than synthetic fabrics, metal tools only, and field blanks that ride along with the cores. The data release should include those blanks so anyone can audit the lab's cleanliness. If a layer lights up in one core but not its blank, good. If both glow, start over. Use what Earth has already given us before drilling new holes. There are vast libraries of archived cores from continental programs and ocean expeditions, quiet basins, low stacks, peat sequences, shelf muds sitting in repositories. Many were sampled for climate or volcanism, not technofossils. Re-examining a subset with our toolkit is the fastest way to test the null hypothesis. If none of those show a narrow, global, industrial-style package, the case for a prior civilization in the last few million years weakens without a single new expedition. If some do, then we focus resources on replication, dating, and context checks at fresh sites. Pattern recognition helps, but it cannot lead. Machine learning can flag thin anomalies in multivariate datasets, places where data double microsphere dips, while magnetic susceptibility jumps and platinum twitches. But the models must be trained on known natural layers and our own modern band to learn. The difference between a volcano and a freeway. The algorithm is a sieve. The verdict is geochemistry plus context. Field strategy should respect the planet we are asking to testify. Lakes and caves lie in protected landscapes. Shelves sit in fisheries. Peats store carbon we cannot afford to vent. The drills and samplers must be surgical, the footprints light, the permissions rooted in collaboration with local scientists and communities. Curation is part of the ethics. Cores and splits go to public repositories with open data, so the hypothesis can be tested by critics as easily as by champions. Communication matters because extraordinary ideas attract noise. Publish negative results as proudly as positive ones. Build an online atlas where anyone can examine the layers, the age models, the spectra, and the thresholds that were pre-registered. Invite outside teams to attack the most promising horizons with their own methods. The goal is not to find the aliens. The goal is to make the rock record say, as much as it can, unromantically and in public, what would success look like if the answer is no? A map of time, windows and archives where a civilization-length band cannot hide. The last million years of high-resolution lakes, caves, peats, loess, and shelves. The calm mid-Pliocene. The noisy mid-Pleistocene transition. The younger Dryas microscope. What would success look like if the answer is maybe? 3 or more well-dated sites on different continents with a shared sub-century horizon, carrying the package and dodging every natural context we know. In either case, the outcome is valuable. A null result teaches how lightly one must live to pass invisibly through stone. A positive result would be the most important scientific discovery in history, and it would be announced with graphs, not headlines. The Silurian Hypothesis began as a thought experiment to hone our tools. A global project turns it into a falsifiable search. We do not have to prove a negative. We only have to show that the best shelves in Earth's library lack the kind of thin, loud band a civilization cannot help but write. If those pages are clean, the case for being first strengthens. If they are not, we follow the evidence wherever it leads, with the humility to let the rocks overrule our stories. In the end, the Silurian Hypothesis isn't a myth about secret empires. It is a method for asking sharper questions of a noisy planet. It reminds us that stone forgets statues but remembers chemistry, that cities crumble but carbon ratios linger, and that history written in mud is thin, global, and stubborn. Reading those pages, the soot, the xenospheres, the catalytic metals, the isotope accents, we learn something about ourselves too. How quickly a species can change the air and how slowly the planet heals. Perhaps no one came before us. Perhaps Earth hosted only the long patience of microbes and forests, the thunder of volcanoes, and the occasional stone from the sky. If so, that is both a relief and a responsibility. We are the first to hold the pen and know that we're writing. We can choose a whisper or a shout. We can push ancient carbon into modern winds, or we can live on flows the planet already budgets for. We can scatter metals and halogens like confetti, or we can keep them in tight circles that return to use instead of drifting into mud and peat. And if someone did come before, their best lesson may be the one we almost missed. Success hides itself. A civilization that mastered restraint would leave little more than a narrow line, a brief, planet-wide modulation in the chemistry of stone. No monuments, no myths, just a signature that says, quietly, we figured it out. We turned our engines down. We stayed. So we keep looking, not for headlines, but because science is how a species learns to be honest with time. We drill and we read and we test our tools against Earth's forgeries. We publish null results as maps of where a predecessor isn't. And with each clean page we pass, the mirror turns back to us. What story do we want to be a warning line, hot and jagged, or a careful seam that hints at long memory and longer futures? When you stand outside at night and feel the planet breathing under your feet, remember that the rocks beneath you are older than cities and kinder than gossip. They will keep our secrets, but they will also keep our choices. If we are first, may we be wise. If we are not, may we be worthy of the company. Either way, the task is the same. Make a world whose history reads like a promise instead of an apology, and leave the kind of trace that lets the next readers begin a little higher up the hill.